Welcome to a new video about analog filter design. In this example, we will discuss the Chebyshev response, Butterworth response, and the Bessel response, and we will compare the results for these three filter responses. Of course, we will see how we can determine the required filter order and realize our circuit using Sallen-Key filter circuits. Of course, we will see everything step by step in our calculations and verify these in SPICE simulations. So our design objective: active low-pass filter. We need to use a Sallen-Key filter circuit, and our final design will also calculate the actual stop and attenuation we have. The specifications for our filter: the maximum passband ripple, a max, must be 2 dB. The minimum stop and attenuation must be 50 dB. The cutoff frequency is 100 Hz and the stop band frequency is 600 Hz. So that means at 600 Hz we need to have a minimum attenuation of 50 dB. That's actually the connection between these two specifications. So let's look at our solutions. The first step is our filter order, and we start first with the Bessel response, and for that we don't have a simple formula. For that we also use the graph as shown here. So this is the horizontal axis, which is called the transition sharpness, and the vertical axis is shown here, the attenuation you get in the stop band region. And you see here the first order up to the 10th order, you see the different graphs. So we will see how we can use these graphs in order to calculate the required filter order. So we start with the Bessel response. You're looking at the transition sharpness, which is our ratio of the stop band frequency and the cutoff frequency for the low-pass filter design. That means 600 over 100, so that means actually 6. So we need an FR of 6. And we know that we need a minimum of 50. So we have now these two values. Now we can now make this 6 here, so we make a vertical line, this red line. And we have here the blue line, which is our 50 dB, between the 60 and the 40 dB here. So we see here an intersection, which is our green dot here. That means it is now between the 4th order, above 4th order, and below 5th order. That means we need to go above 4th order. That means we need to make a 5th order in order to fulfill the specifications for our Bessel response. So that means from the graph we need an NS5 and for this specific transition sharpness. So that means N Bessel, so I denote that by NBS, which is down here 5. Okay, the next one is about the Butterworth response. For that we have the formula, so we can do it analytically. We go first to the epsilon p, which is connected to a max. That is then, in this case, 10 to the power 2 over 10 minus 1 in the square root, and that will result in this value. In a similar form, you use now the epsilon s, which is connected to a minimum, which is then 50 dB. And if you now do the math here, you get here almost 316.2. Taking this together in the formula of the Butterworth response low-pass filter, and you get here now the values. And this is now the filter order we want, which is 3.36. So we need to, of course, go to the integer value. That means we need to always round it up. That means the Butterworth response filter order must be 4. So that means N Butterworth BW must be here 4. So you see actually already the Bessel response requires a 5th order, and the Butterworth response for the same specifications, a 4th order, so lower order actually. The next one is about the Chebyshev response, and it is at 2 dB. So that means we also look at the Chebyshev response 2 dB ripple. Now the exact same calculation for the epsilon p and epsilon s are also valid for the Chebyshev response, so I just copy them. And taking this together, we only use a different formula here. Instead of logarithmic, here we use the R cosine, so inverse cosine hyperbolic function. Again, the epsilon s, epsilon p, the stop band frequency, and the cutoff frequency. Everything is actually exact same. If you now do the math here also, you get here now 2.7 approximately, which is then, again, rounded up, saying the N of the Chebyshev response must be 3. So you see actually the filter order goes down when you change your filter response. Okay, so that means we have a lower order. So we have actually achieved the same goal of the attenuation and the cutoff frequency by making actually a lower order filter circuit, which is of course perfect if you want a lower count for your components in your circuit. Now, summarizing here the Bessel, the Butterworth, and the Chebyshev response here. Now for the Bessel response, in order to make the circuit realization, we need to cascade a 3-pole and 2-pole Sallen-Key low-pass filter circuits. That's actually shown here. So this part here, the first stage here, using the R1, R2, R3, and the C1, C2, and C3, and this unity gain feedback operational amplifier is our first stage, which is a 3-pole Sallen-Key low-pass filter. And this part here with the R4, R5, and C4 and C5, and again the unity gain feedback operational amplifier is our second stage, and this is a 2-pole Sallen-Key low-pass filter. Now here we need to, for the Butterworth response, a fourth order. That means that cascading of two 2-pole Sallen-Key low-pass filter circuits. Again, the same thing here, but then twice actually here. So you see here the configuration. Now for the Chebyshev response, we only need a third order. That means we can do the job using one 3-pole Sallen-Key low-pass filter circuit, and that's actually shown here. So it's actually just this one, and you place it here. So you see actually the number of components goes down if also the filter order goes down. That is of course beneficial. Let's start with first the Bessel response and calculate the components there. So for that we need to look at the Bessel response table. You see here the filter order going from 2 to 6. And you see here the number of sections, what kind of a section should be 2-pole, 3-pole, or more than 2-pole, 3-pole. And you see also here the C1 over C, which is then the scaling factor C, and this is the capacitor C1 you need to calculate in your filter. The other ratios are for the high-pass filter design, which is actually this row. Okay, let's go in detail what we want. Of course, we need to have a fifth order. That means we need to look at this row. You see here the 3-pole, you see also the coefficients, and also for the second stage, which is our 2-pole Sallen-Key low-pass filter. It will be now clear how we need to use these values from the table. Now, in order to continue, we can make the selection by setting the R1 is equal to R2 is equal to R3 is equal to R4 is equal to R5, and then define it as R. That is the exact same, and we just pick a value here which is convenient, let's say 1 kilo. Then the scaling factor comes into play, which is our C, which is then 1 over this R omega C, which is our cutoff frequency in the radians per second. And we have selected our R. We can now do 2 pi times the FC, and that means actually this 1 over this 1000 ohms, and then 2 pi times 100 hertz. That will result in this, the scaling factor C, which is then 1.59 times 10 to the power minus 6. This is approximately the scaling factor we need to use. This C is exact same C here as the table which you see here. Now from the table, from the parameter scale factors, we can say the following. For a 3-pole, we see C1 should be then 1.10 times C, which is actually this ratio, needs to be the 1.10. And this, if you now do the calculation using the C we just calculated, you get here 1.607 microfarads approximately for the value of the C1 we need to use in this circuit. Now C2, then you need to use this 0.8712 times C again, and you will get for C2 value of 1.387 microfarads. Now continue with the C3, which is then using this value, which is then 0.3095 times C. That will be then C3. Again, looking at the ratio, C3 over C must be this. So rewrite that, you get this one. Again, substitute the value here, and using the scaling factor we have here, that means 492.6 nanofarads. Now the 2-pole part, which is then actually this second stage. Now we go to the C4, that is then 1.0410 times C. Again, the same C, and you just substitute here the values, you get here almost 1.66 microfarads. And the final one, C4, for that we need to use this 0.31 times C again, and you get here 493.4 nanofarads. So we have now the 5 capacitors for this circuit for our Bessel response design. So our simulation circuit is then shown here. You see here the C1, C2, C3, C4, and C5. So those are the calculated values from here. And the R's are everything. So 5 R's are all 1 kilo. You see also the 2 operational amplifiers in the unity gain feedback configuration. Okay, now we do the circuit realization for the Butterworth response. You see here now the component values. Again, we will use a table, but now specifically for the Butterworth response. Now the values will be here different. Again, going up from 2 to 6th order. Now we need to look at the 4th order region. And now you see here a 2-pole section, which is the first stage, and again a 2-pole section, which is then our second stage. Which is really similar to the calculation we just did. Now we again select the R1 up to R4 equal to each other, again 1 kilo ohm, and we define it as C, and we calculate again our scaling factor. This is all the same as we have done it for the Bessel response. Now we need to look at the battery response table and then use the two-pole part. And this is really the same procedure as we have done it for the Bessel response. Now we will use 1.082 times the C for the C1. And that will result in this value, which is then almost 1.7 microfarads. And for C2, you will use this one, 0.9241. And that will result in 1.47 microfarad approximately. For the second stage two-pole, you need to use this 2.613, and then you will get here almost 4.16 microfarads. And the C4, which is our final value, that will be then here 608.8 nanofarads. Okay, now we have the four capacitors for this circuit also. And the simulation circuit is shown here. You see here the C1, C2, C3, and the C4 as we have it calculated here. And the four resistors we have taken as 1 kilo. The final one, which is our Chebyshev response 2 dB ripple, third order, the 3-pole low-pass filter is shown here. Now again, the component values. Now we look at the Chebyshev response 2 dB ripple coefficients. These are also different than the other two. So we look at the third row. Here we have here 3 values we need to use. So again, the same, but now we select again the R1, R2, and R3 exact same and define it as R. Again, selecting 1 kilo ohm. The same scaling factor, that doesn't change because we look at the same cutoff frequency for both all cases. Now we look at the Chebyshev response table and the 3-pole. That means C1 will be then 27.82 times the C. We just, of course, have it here. That will be then 44.28 microfarads. The C2 will be then 3.113 times the C, and that will result in the 4.954 microfarads. And the final one is 0.03892 times C, and that will result in this 61.94 nanofarads. Okay, now we have also the 3 capacitors here for this circuit, and the simulation circuit is actually shown here. So again, the resistors are all 1 kilo ohm, and the C1 here, C2, and the C3. Okay, let's now look at the situation for the actual stop band attenuation, because that's actually what we needed. So we have done the required component value calculations. We start first with the Bessel, and we have a 5th order, and for that we need to use this table which says the Bessel response transfer function coefficients. You see here the 5th order coefficients from A0 up to A4, and we also have this capital N, which is our coefficient in the numerator. So the transfer function has then the N5, which is our 5th order. This is the coefficient in the numerator, which is then 945. And the denominator polynomial is given in general like so, which is the 5th order polynomial. So s to the power 5 up to A0. So you see here the coefficients. And we can now read from this table what the A4 must be A3, A2, A1, and A0. So that means actually this one. Now we need to use these in order to go to the actual stop band attenuation calculations. Now the transfer function for a 5th order low pass filter for Bessel response is then the N5 over this polynomial here for the D5. That means in the Laplace domain or Laplace parameters like so. Now we need to go to the J omega domain, that is the steady state analysis. So we need to convert the S, or we select S is equal to J omega. So you substitute here the S is equal to J omega, and you end up here by looking actually to the values here. You actually come to the real parts and the imaginary parts. I can show you a couple of them. This, for example, will be then 105 times the J omega in the quantity cubed. And that will be actually this one, because it will be then J omega times J omega times J omega will be then minus J omega cubed. That's actually why you have this minus, and the J is here outside the parentheses. And this one, for example, is a pure imaginary with this 945. That's actually this first term. This is a pure real part, that's actually all the way here. And this one here, which is actually then the J omega times J omega, which is then minus omega squared, with of course times 420. That's actually what you see here. So in a similar form, you do the other parameters and you collect the real parts and the imaginary parts in this format. Now the absolute value of this expression is just the amplitude of this part numerator divided by the square root of the square of the real and imaginary part added together. That's actually shown here. Now we need this expression because we need to go to the value of the stop band attenuation First, we need to solve an equation which is set here. So it says actually the following. The transfer function here defined at the 0 frequency, which is then 0 radians per second, divided by the square root of 2, which is actually the definition of the cutoff frequency. So we need to solve this. How do we do that? And that should be then 1 over the square root of 2, because the gain at 0 radians per second is 1. You can also see that from here. If you substitute here for S is 0, you get here 945 over 945, which is 1. That's why we have a 1 over the square root of 2. Now, this is now the expression here. You just copy that, and that will be then equal to 1 over the square root of 2. So we can solve this using a solver, and that will result in an omega, which is then approximately 2.42741. And that is now defined as the T sub n, which is called the time normalizing or normalization factor. This is an important parameter we need to use, because now we go to the scaled transition sharpness using this value and the ratio of the stop band frequency and the cutoff frequency we have used before in order to calculate the filter order. So we use a Tn times this Fs over Fc, and that will result here in 14.56 approximately. The next one is about the stop band attenuation. This is now the formula here. You see here the minus 10 logarithmic of this numerator squared divided by an alpha squared plus beta squared. So what is this all these parameters meaning? Here the alpha is a real part of our denominator polynomial, which is actually this one, of course, in the j omega domain, which is evaluated at that scaled transition sharpness. And the beta is our imaginary part of that denominator polynomial. So the denominator polynomial, which is the 5 in the j omega domain, is actually this, which is actually completely this one. And if you look at now the real part, which is this part, and now you need to also evaluate that at the capital letter omega r, which is actually shown here. That is actually the alpha. So you see that actually clearly here. If you now substitute there 14.56 approximately, that's actually what we do here. So you just do everything here step by step, and you get here this value, which is then 586,799. In a similar form, you do the beta, which is the imaginary part. You take only this part. You see that here, and you substitute for the omega, the capital letter omega sub r. Substitute there the value of 14.56. That's actually shown here. And you get here 344,718. Now we have the necessary values, because this is already known, because that's N5, which is here, this 945. So the actual stop band attenuation for this Bessel response should be then minus 10 log, and then in the parentheses, 945 squared divided by the alpha squared, which is here, and also the beta squared, which is there, and that will result in almost 57.15 dB. Okay, which is larger than the 50 dB we needed, so it's actually according to the required specifications for our filter design. Now, let's take that here for the Bessel response and now do the exact same procedure, but this is done much faster for the Butterworth response. For that, we need to use this filter formula for our Butterworth response. The A minimum is 10 log 1 plus the stop band frequency over the cutoff frequency to the power 2n, and n here is the filter order, which is in this case 4. So in this case, this is indeed much faster. So if you now substitute here the values, 600, 100, and 2 times 4, which is 8, that will result in 62.25. So you get here more attenuation using a Butterworth response, even though you have a lower order, which is actually interesting. Now the passband frequency for the Chebyshev response, we need to calculate that first. That is given by this expression for the low pass filter. The cutoff frequency is required, the epsilon p, and the filter order. We know the epsilon p and the filter order from our calculations. So that's actually the epsilon p, and the filter order was 3, and this is 100 Hz from the cutoff frequency in the specifications. If you do the calculation here, you get here 96.82 Hz, which is then a little bit smaller than the cutoff frequency. Now you also get at this frequency our gain of minus A max or minus 2 dB. That's actually the location for this ripple. Now then we can calculate now the A minimum for this Chebyshev response, which is this complicated formula, but it's a little bit complicated than the Butterworth response, but still much faster than the calculation we have done for the Bessel response. Again 10 log and then 1 plus again the epsilon p squared. Now you see here again the cosine hyperbolic function squared, and then the filter order and the inverse of that cosine hyperbolic function, the stop band frequency and the pass band frequency that is required. When you now substitute here the values, you get here now 57.07 dB. You see here that all three filter responses and designs have a higher attenuation than the 50 dB we need to have, so this is indeed as we wanted, but some filter response will create more attenuation. That's actually what we see here for the Butterworth response. Okay, let's now do the summary, which is the calculation. Here you see the different responses: 5th order Bessel, 4th order Butterworth, and 3rd order Chebyshev response with a 2 dB ripple. And you see here the achieved stop band attenuations for each response. Okay, now look at the simulation results. You see here now the plot. In red we see here the Chebyshev response, the green is our Bessel, and the blue one is our Butterworth. Now you see also again the calculations here, and you see also the cutoff frequency here, which is indeed at 100 Hz. So you go down from this 0 dB, which is a unity gain, to -3 dB that happens at 100 Hz as we wanted. So that is fantastic. For Bessel response, we read here in the simulation almost -57 dB at 600 Hz, which is close to what we have calculated, a little bit smaller. For the Chebyshev response, we see here -57.07 dBs at 600 Hz, so it is actually exactly as we have it. And for the Butterworth response, we see at same frequency -62.25 dB, which is also exactly as we have calculated. What you see is, and what you recognize, is the following: the Chebyshev response is actually steeper in the region after the cutoff frequency, and then the Butterworth response is actually catching up and then has a steeper decline here in the stop band region. But the Bessel response is always much slower in the decreasing in the stop band region, but it will eventually catch up with this Butterworth response after some time, which is then at 600 Hz. So it depends, of course, what you prefer and what kind of a ripple you accept. If you accept no ripple at all, then the Chebyshev response is of course not the way to go. But for this design, the cutoff frequencies are as we wanted, and the minimum required attenuation is also achieved using these three filter responses. So we have actually achieved our goal. And we have seen that we can achieve a minimum attenuation we want using a filter order which is much smaller. So if you want a filter order which is smaller, so lower order, and you don't mind if you have 2 dB or 1 dB ripple, then you can go for the Chebyshev response and you have 57 dB approximately attenuation, and you don't need a 5th order but a 3rd order in this case. Alright, it was our example considering the active low-pass filter design for the specification, and compared the filter orders for the Bessel response, Butterworth response, and the Chebyshev response, and also looked at the achieved stop band attenuation. If you have any questions, comments, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.